The next speaker in this session, and I think that going on conspiracy number search, of course, I thought for a very short while when I was still naive that proof number search would be the end to the discussion about conspiracy number search. But what he will show and talk about is that conspiracy number search adds something to proof number search, which is you know actually what's going on in individual nodes, while proof number search is completely oblivious of that. So very interested to hear what Jacob has to say about feature strength and parallelization of sibling conspiracy number search.
Okay. So I will go to say how we adapted conspiracy number search for our hex program, because we had a very strong PN search solver over there, but we had also some evaluation function. So conspiracy number search should fit there well. So first I will just briefly give the intuition how the conspiracy number search works. Then I will say about our simple modification. And even we made some modification, we had to make many optimization in order to be competitive to other state-of-the-art programs like Pawlewicz. And it is the case that we are competitive, and I will show it in results. So maybe let's first view into, let's have a look into proof number search. So normally, let's say we have a minimax tree, and we have an evaluation function applied to leaves. Proof number search is only interested whether this evaluation is plus infinity, minus infinity, and everything else. And it tries just to expand such leaves in order to move the minimax value in the root towards plus infinity or minus infinity. And it navigates, guides the search tree using two statistics for that purpose. So one statistic is proof number, is how many non-terminal leaves has to be non-terminal leaves with value smaller than infinite, so not proven yet. How many leaves has to be proven in order to prove the root. And this proof number is similar statistic, but but opposite. And yeah, instead of trying to reach a value plus infinity, which is difficult target sometime in the middle of the game when we are far from the end, we can change the target for something smaller, to say to Vmax. And analogously for min player, so minimizing player, that instead we would like to achieve some very simpler goal Vmin. And we just set this target temporarily for one iteration. And so we change what min and loss win for one iteration. This is just the idea how to generalize in proof number search, and we arrive at conspiracy number search. But to make it work, we have to store a much more complicated statistic in a node. Instead of single proof number, we have to store proof numbers for each possible evaluation V of the node. So Pn applied to V counts the number of leaves we should change in order to change the minimax value from something smaller than V to V. And actually it means that we have to store in the node entire function. Not only single number, but entire function. It can be viewed in that way. So let's take a look how these proof functions can look like. In a node, this is the blue function is I will call it proof function. It's like that. Below minimax value of the node, it is always 0 because we already achieved the goal. Above minimax value of a node, this function slowly increases. So here we need just change the value of single leaf in order to increase minimax value. And for larger targets, we probably can should change more leaves. And the last step here in this staircase function is actual proof number from proof number search. This proof number is the function which is similar, but it is in opposite direction. And let's say this is our proof number function, this proof number function in the root. So the main thing in conspiracy number search is to choose these Vmax and Vmin values, which we call maybe a little bit misleading the search interval, but let it be the search interval. And for that we have to define how difficult these targets could be, these Vmax. So we say that we don't want a target more difficult than such that we need to expand at most Pmax leaves. So Pmax is some threshold for the proof number of the Vmax max target. And similarly, Vmax is a threshold for the number of leaves we would like to expand for a min target. And then we choose Vmax and Vmin. So Vmax we choose as the highest possible value we can reach by changing only at most Pmax leaves. And this interval changes from iteration to iteration, and after some longer search, the proof function, this proof function changes in the root, and this interval can become very small, and maybe we should increase this interval because the search is going very, very deep. It should explore more variation. So in order to do it, we have to make this interval larger. And we introduce two more parameters, delta P and delta D. They denote the minimal distance from the minimax value of the node for the target. For here, delta P is this distance. Here, Vmax is large enough, but here Vmin is not enough. So it should be smaller because it is within this delta P distance from the minimax value. And then when such situation happens, we want to move the target further. So we increase the number of leaves we are interested in to the first step here, and we choose Vmin as the smallest possible value which can be achieved in this number of exports of leaves. So this is the main thing in this conspiracy research, choosing the interval. This is our proposition, how to do it. Yeah, that's an intuition about conspiracy research. I don't want to go into details, it's too complicated. Yeah, we have modified this conspiracy number search into algorithm called Sibling conspiracy number search. So, in hex, for game of hex, probably most of you know it, but yeah, players here play stones alternatively, and the target is to connect opposite sides of the board with a chain. So here, for instance, white player 1. And in hex, we have very good knowledge. So to evaluate a board, we apply electric circuit resistance. It is very good evaluation function. It is further enhanced by virtual connections. So virtual connections, what they are. So in hex, it is possible to solve some sub-games. Then you can combine these sub-games into larger sub-games and get a lot of knowledge. It's a very strong machine. And we have a very good evaluation function, which, when we applied it to conspiracy number search, it wasn't. It didn't work well. Why is that? It's possibly because this evaluation function doesn't compare well position in a very different position, which are in different, very distant branches. But this electric circuit gives us another information. Mainly, it also computes some cell energy drop in each cell, and that measure compares moves in given situation very well. It was used in our solver. It makes stronger, very much stronger by sorting moves, and we found it is very reliable heuristic. So we try to design an algorithm which just has a very good local heuristic, comparing only siblings. And how to do it? So we did it by introducing special, strange-looking evaluation function, which we given a name, siblings comparison evaluation function. So in heads, a move is putting a stone in a cell. So we have cell energy for a cell, and first we choose a cell with the highest energy. So the higher energy is, the better move is. So the cell with the highest energy, say C0, is the best possible move in given situation. And we introduce relative error of a move. And this is relative error to the best move. There's some function using energies. There are other possibilities also. But what is important here that this relative error for the best move, so for C0, should be 0 because it is optimal move. And the worst move is the higher relative error should be. So in other words, relative error says how much we deviate from the optimal play according to this local information, according to this cell energy. Okay, having a measure, which we call relative error, we construct evaluation function. So for a leaf, here, we want to apply evaluation function, and we look into path leading from root to a leaf. So let's say we evaluate it from the point of view of a max player. So if a max player makes a move with some error, so it deviates from optimal play by E1, it is bad. So we should subtract it from the evaluation function. For min player plays error E2, so it introduces some error. It is bad for opponents, so good for us. So we add it to the evaluation function, and so on. And so our evaluation function is an alternating sum of errors. And here, this is an evaluation function, and applying this evaluation function to conspiracy number search, we call it the algorithm siblings conspiracy number search. Why it deserves a new name? So yeah, this was a theory, but maybe it's better when I give some intuition how this algorithm works, because this evaluation function implies very nice behavior of the search. So let's start. Let's say we have two pairs with black and white. How the algorithm behaves at the beginning. So we have root. First, it will expand root. Here we have one move with relative error 0, which means it is the best possible move by local heuristic. And what the algorithm does, it probably would expand cheater, but it will investigate that child. So it expands that child, and again it will choose a child here with which is the best one, so with relative error 0, and it will continue expand nodes until it reaches some terminal state. When it arrives at the terminal state, say it is a win for black, then white is in trouble. So I played optimal moves according to my local heuristic, but it got wrong. It got wrong. So I have to deviate from that line of play somewhere, and where I can do it. So everywhere on that path, and when I should change my strategy. Well, I should choose move which introduce the smallest possible error. 5 minutes? Yeah. Okay, and let's say it is zero. And then algorithm switches to the branch. And then it will explore this line of play. And it will go until to some terminal state, and for that terminal state, it is a win for white, and this one, then white has to deviate. Is in trouble. Has to change the node to white. So black is in trouble. So black has to change his strategy somewhere, and possible places are here, here, here. And the top part is he tries to minimize error. Here, white already introduces error E0, so it is enough to minimize difference 1 or 0. Let's say it chooses that move, and white then has a response for that situation somewhere in the tree. In general, after many iterations, this algorithm creates some strategy tree for both players with some optimal play, and if someone is in trouble, then algorithms magically jumps into the most promising response somewhere in the middle of the tree. It works magically, and this is what we observed. All right. We made a few optimizations. The most important one, when we initialize leaves. In a leaf, the proof function looks very simple. So it is 0 below minimax because we don't have to do anything, or 1 if for greater values. So, but by intuition, if you want to reach some higher minimax value, you need usually you can expect that you will need more effort. So we changed initiation of a leaf by introducing a more complicated function. So we say that if the minimax value is, to reach minimax value greater, we probably will need two leaves. And this function looks like exponential one. It is very strong modification of conspiration number search. It changes the strength of the conspiration number search a lot, which I hope we hopefully show in the results. We also, because these local heuristics can be wrong, and we have to diminish sometimes its impact. And one of the way of doing is when some move is searched anyway, even if the error is high, then probably local heuristic was wrong. So we gradually diminish the value of the error depending on how much work we done in that node. This is one optimization. Another, we use strafe, but a little bit differently. So in given node, when we get to many terminal situations, we look for given move in how many wins he was used, in how many winning plays he was used, and how many losses, and we change the error according to that using that information. And the more information we have, the more we switch to rank. So at the beginning we have the initial error by local heuristic, and then we switch to rank. So it's opposite to what we do in CTX. Okay, and now I can show you some results. So, having this, we had more optimization, but I'll just focus it on a few. We had a lot of parameters, so we decided to optimize them by clock. We faced it against Mohex and we use 30 seconds per move. We arrived at parameters Pmax 3 and Dmax 4. So they are very small. So the search is very narrow and it's good. And delta P and delta D for such small timings were not important. And we got winning rate of 60%, which is a lot. And yeah, we tested some variants in order to see which parameters are the most important. And when we resign from this initialization of multi-step function to the simple one, which is plain conspiration number search, then results are just bad. What else is important? When we increase the time limit, so 60 seconds per move, it showed up that that parameters found by clock are wrong. They are not correct. For instance, it is better to switch off rave. So why is that? Because we think that a clock just over-optimize those parameters. So it's better to switch off rave or increase Pmax, Dmax, because when we have more time, we can search a little bit wider. I have 2 more slides about results. So we also, I can mention that we also produce at a high quality player. We apply at our our parallelization of proof number search, which was good for proof number search, but for conspiracy number search, it doesn't scale so well. So we are not as good as on CTS here. But we use clock settings maybe for when we have more time, we should change parameters. We are investigating it, we have some ideas, maybe we will do better. And yeah, and final comparison, we play it against Mohex, the strongest current program, using tournament settings, 12 cores, 90 seconds per move, and we achieved winning rate 0.448, so it is close. As a starting point to this, Mohex is heavily optimized over the years program, so we are just happy that after just few optimizations we got such a winning rate. And as we spotted that these parameters were wrong, we increased them and we were able to get some higher winning rate. So we have to play parameters differently than by clock. Okay, maybe.
Thank you so much. Interesting work on conspiracy research. Questions?
Could you go back to maybe 12 or 3? Right. Okay, go up. Okay. Yeah, right. You choose one of them from those are candidates.
Yes.
But what's the rule to choose among these?
Okay.
Okay.
So because for the evaluation function, white playing a move with error higher than 0, it will introduce error E0 to the evaluation function. So it will reduce the from the point of view of white player, it will reduce the value of evaluation function. And
my question is, yes. So, but the error here might have different meaning from this error.
Yeah.
Because a different label.
Maybe. But if we trust this local heuristic a lot, then it is better to because it is possibly actually the case that playing here will result in some weaker position than playing here, and we just doesn't distinguish the depth of the game. So how many stones were played. We just have a huge set of positions, and we just want to be in a position which is the most promising. We ignore that. We should do some search in the top. But we achieved that the goal that we search a little bit more in the top by increasing thresholds Pmax and Dmax. We achieved that.
Okay, next question. Ingo?
Your hex experiment, what was the board size?
11 by 11.
Does that give you the information? Why is the board size important?
Yes, 11 times 11 is still near to the case where you can get exact values, and yes, 13 times 13 is more what people like to play. Yes, it was simply good to know.
Solves for 9 by 9, isn't it?
What's that?
9 by 9 we solved it by a solver, and solver was a strong player just using proof number search, and we're using simple when we used proof number search as a player, but the problem is when you have to terminate in 1 minute and you didn't solve a position, then you have to choose somehow a move. So we use simple heuristics, play a move where the most visits were done. It was a very strong player, but for 11 by 11 didn't work, so we have to change approach somehow and we used conspiracy number search.
Time for one last question. Yeah.
In your picture here, you show alternative crystal on or two side. Yeah. Okay. What if the result is lost? Okay. What would the chip?
Now here is a loss for black.
Right.
Yes,
So
but
do you choose some different one? Consider different.
if it was a win for black,
Right.
So-
Okay.
it was a win. Here is a.
Okay. Sorry.
Later is an example. It's a win for black. Then white either can negate here, but he just will increase more his error. Already introduced error is 0 or somewhere here.
Okay. Thanks so much. We have another break.